In this video, we're going to talk about Shor's period finding algorithm. Okay, so let me give a little overview of where we are and what we're going to do today. So in the last video, we introduced the Fourier transform over the group of integers modulo n, and we also showed how to come up with a quantum circuit to implement that Fourier transform that just had order of log n squared many gates. Okay, so a very efficient quantum circuit to implement the Fourier transform. So today we're going to look at an application of that, an application of the Fourier transform over Zn, and that application is Shor's period finding algorithm. So we're going to start off with finding the period of what I call a simple periodic function. So this has all the main ideas that are needed, all the quantum ideas that are needed for Shor's more general period finding algorithm. But actually, the application of simple periodic functions does not suffice for the integer factorization algorithm. So after we do the simple periodic function case, then we're going to generalize that to what I call almost periodic functions. And that is the case that's actually needed for the application to integer factorization. Okay, so a future video will talk about how you use period finding of an almost periodic function plus some number theory to actually do integer factorization. But in this case, we're just going to focus on Shor's quantum algorithm to find the period of a simple periodic function. Okay, so what is a simple periodic function? So we call a function f from the integers modulo n to the set of integers from 0 to n minus 1, a simple periodic function if there is an s such that f0, f1, f of 0, f of 1, etc. up to f of s minus 1 are all distinct. And also f of x is equal to f of x plus s for all x in Zn. Okay, and the addition here is done modulo n. Okay. So a couple comments. The range of the function doesn't really matter. So we're just using 0 through n minus 1 here. It could really be anything. It doesn't really come into the analysis. The second thing to note is that these two conditions together actually imply that S divides N. Okay, so that's very important for this simple periodic function case. So I think you'll see why if we just look at an example here. So let's look at an example. Again, these are our two conditions to be a simple periodic function. So in this case, N is 9 and S is 3. So you see that the function just repeats red, blue, green, red, blue, green, red, blue, green. And you see that, that f is red on the set 0, 3, and 6. So when x is 0, 3, or 6, f takes on the value red. F is blue on the set 1, 4, 7, and f is green on the set 2, 5, 8. Okay? Now, just to kind of foreshadow what's coming later when we eventually get to talking about the hidden subgroup problem, you see here that the set on which f is red is actually a subgroup of Zn, and this is a subgroup generated by S. Okay, so this set here, it's closed under addition modulo n, right? Because 3 plus 6 is 9, modulo n is 0. So this set is actually closed under addition modulo n. This is a subgroup of Zn. And the other sets here, well, they're not subgroups, but they are just shifts of this subgroup generated by S. So here we just shift all these elements by 1, we add 1, and here we shift all these elements by 2. So another way to phrase these two conditions is that f of x is equal to f of y if and only if x minus y is equivalent to 0 modulo s. Okay, let's also look at a non-example to give us a feel for what being a simple periodic function means. So in this case, s is still 3, but n is 7. Okay, so we don't have that s divides n. Okay, so the function again is red, blue, green, and then red. Okay, so you see that now because s does not divide n, f does not wrap around properly, right? So f of 4 is equal to blue, but f of 4 plus 3, so 4 plus 3 modulo 7 is 0. Okay, so f of 4 plus 3 is equal to f of 0, and that's red. Okay, so because s does not divide n, um, we don't have that f of 4 is equal to f of 4 plus s, okay, which is the property that we required for a simple periodic function. Okay, so basically the issue is this wrapping around. So in this case, f does satisfy that f of x is equal to f of x is equal to f of x plus 3, as long as you don't wrap around. So as long as x plus 3 is strictly less than 7. Okay, so a function with this property, and also still the property that f of 0, f of 1, up through f of s minus 1 are all distinct, we call such a function an almost periodic function. Okay, and this is the case that will actually be needed for the application to integer factorization. But so as I said, we're going to start out with the simple periodic function case. So let's go ahead and define the simple period finding problem. And as I mentioned, this problem already has all of the quantum the ideas that are needed for the quantum algorithm. And this case is also very elegant mathematically. Okay, so the generalization to the almost periodic function case, it doesn't really require new insight. It just is a bit more messy in a technical sense. Okay, so I really like this simple period finding problem. Okay, so let me precisely define what the problem is. So the problem is we're given a simple periodic function and we want to find its period. Okay, so this is basically a direct analog of Simon's problem. Simon's problem, we also had a periodic function and we wanted to find its period. The only difference is that in Simon's problem, we were working over the group z2 to the n, and now we're working over the group the integers modulo n. Okay, so I just want to point out that the constraint of being a simple periodic function, it is quite a strong constraint. It does imply this condition that s divides n. So for example, if we're working modulo 2 to the little n, well, I mean, how many divisors are there of 2 to the little n? I mean, you have to be, like 1, 2, 4, 8. You have to be a power of 2 to divide 2 to the n. Okay, so there's actually only little n many divisors here. Okay, so in this case, this simple periodic finding problem, when you're working over z 2 to the n, when capital N is 2 to the little n, is actually pretty simple, okay? Because you can just check every possible divisor, right? You query f of 0, and then you query, f of 2. If f of 0 equals f of 2, then you know that s must be 2. Then you query f of 4. If f of 0 equals f of 4, then you know that s must be 4. Okay, and there's only n many such s that you have to check. So this is actually quite an easy problem, even for a deterministic algorithm. Okay, so the interesting thing is that when you go to this um, almost periodic function case, then that becomes a hard problem classically, but the quantum algorithm generalizes to that case as well. So let me say a bit more about the setup. We're again working in the query setting. So we have this simple periodic function f, and we assume that we have an oracle OF that implements f for us. And in what way does OF implement f? So that's given here. So x is an element of Zn. We just represent elements of the range by bit strings. Okay, so Z here is a bit string. And what does OF do to the basis state, ket x, ket z? Well, it just XORs the value of f of x with z in the second register. Okay, so here's z and f of x, they're both m-bit strings. This is the bitwise XOR. So this is basically the same action of the oracle that we saw in Simon's problem. Okay, great. So let's go ahead and look at the quantum algorithm. So the first step is very familiar. We create the uniform superposition on the first register. We can do this by applying the Fourier transform. Okay, so we create the state. Then we apply the oracle. The second register here is just the all zero string. So once we apply the oracle, then we have that writes f of x to the second register. Okay, so now we have this uniform superposition over all elements of Zn, ket x, ket f of x. Okay, now I'm going to keep with our running example where capital N is equal to 9 and S is equal to 3, and this function that I defined earlier on the slide in the table. So in that particular case, the state that we have is just 1/3 times ket 0, ket red, plus ket 1, ket blue, plus ket 2, plus ket green, etc. Okay. Okay, so as we did with Simon's algorithm, we're going to rewrite the state by grouping together the terms by the value of f of x. Okay, so here I've put together all the terms where f of x is red. So which x map to red, that's 0, 3, and 6. Here are all the terms which map to blue. So that's where x is 1, 4, or 7. And then when x is 2, 5, or 8, it maps to green. Okay. And so let's just see, more generally what this is going to look like. I mean, what do we have here? 0, 3, and 6. We have all the elements of Zn that are equal to 0 mod s. Okay, and 1, 4, 7, these are all the elements of Z9 that are 1 mod s. And here's everything that's 2 mod s. Okay. Okay, so let's introduce some notation to deal with this case in the general case. So just let GT be the uniform superposition over all x where x mod s is equal to t. Okay, so I mean, how many x's are there where x mod s equals t? Well, that's just n divided by s. Okay, again, we know that we're in the case where s divides n. So each of these sets, is going to be of size n over s, right? The set of things that are 1 mod s, 2 mod s, 0 mod s, etc. Okay, so our normalization here is square root of s over n, and then we have this, and that gives us the uniform superposition over all x such that x mod s is equal to t. And I call that state GT. Okay, so I'm just going to plug that in to our formula here. Okay, so let's see what that gives us. So, so this is equivalent to 1 over root 3 times the state G0 tensored with red, the state G1 tensored with blue, and the state G2 tensored with green. Okay. Again, why is the normalization here 1 over root 3? Well, I define GT to be a unit vector. Okay, and of course we know that this state overall is a unit vector. So, and I have 3 unit vectors here that are orthogonal. So my normalization here should be 1 over root 3. Okay. And in general, what is the state of the algorithm at this point going to look like? Well, we can just write that as you see on the bottom right. So 1 over square root of s, sum from t equals 0 to s minus 1, the state gt tensored f of t. Okay? Okay, so that's the state that we have after the second step, where we apply the oracle. So as we did with Simon's algorithm, we are now going to measure the second register. So again, this step is not critical for the working of the algorithm. It's just to make our presentation simpler. Okay, so when we measure the second register, what's going to happen? Well, we're just going to see a random value of f, right? I mean, we have a uniform superposition over these states here. So we're just going to see a random value of f. So let's see the value we see is a, and that c is such that f of c is equal to a, and c is between 0 and s minus 1. Okay? So if we do that, then we're in the state gz tensored with f of c. Okay? So for our running example, let's just say we're in the state g1 tensored blue. Okay, now we're ready for step 3 of the algorithm. And as you might guess from the algorithms that we've seen so far, step 3 is going to be to apply the Fourier transform, in this case over Zn, to the first register. Okay, so before we get into the mathematics of what happens when we apply the Fourier transform to the first register, let me just give you a little demo to show you what happens. Okay, so here I'm going to use Octave to do this little demo. So let's work in the case of our running example. So n is 9, s is 3. And I just want to create a matrix whose columns represent these GT vectors that we've been talking about. So this is going to be repmat of I3 n divided by S1. Okay, so if you start the indexing of the rows by 0 here, then you see that the first column is 1 in position 0, 3, and 6, and it's 0 everywhere else. The second column is 1 in position 1, 4, and 7, and the third column is 1 in position 2, 5, and 8. Okay, so this is like our GT vectors, except it's not yet normalized. So let me normalize this. Whoops, I should assign that divided by square root of 3. Okay, so let's check. Yeah, so that should be normalized. You can check that like this. Okay, good. So now all the columns of x are unit vectors. And now we want to apply the Fourier transform to each of these columns. So in MATLAB, we can just, or in Octave, we can just do that with this fast Fourier transform command. Okay, and so Octave uses a slightly different normalization than we do. So I think we should divide by square root of n here to get unit vectors. So let's just check that indeed we have unit vectors. Okay, good. So let's look at y. So this, the matrix y, so the first column here is the Fourier transform of G0. The second column is the Fourier transform of G1, and the third column is the Fourier transform of G2. Okay, so just the columns of each column of y is the Fourier transform of the corresponding column of this X matrix that we've created. Okay. Now you notice something about y. Okay. So each column here, it's non-zero in the same places, right? So it's non-zero in row 0, in row, so 0, 1, 2, 3, and in row 3, 4, 5, 6. Okay? So these vectors, they're non-zero in positions 0, 3, and 6, and they're zero everywhere else. Okay. And moreover, the magnitude of each entry of y is the same. Okay, so if we look at the interiorized product of y with the conjugate of y, okay, so you see that the magnitude of every entry is the same. Okay, and this is going to be a general property of the Fourier transform of one of these GT vectors. Okay, so if we go back to our slides here, then in general, what is the Fourier transform of GT going to look like? Well, it's only going to be non-zero in those positions y where y mod n over s is equal to 0. Okay, so that's what we saw in the example, right? So it was non-zero in positions 0, 3, and 6. And in our case, n divided by s, n is 9, s is 3, so this is 3. So, so indeed is only positions, non-zero in positions where y mod 3 was equal to 0. Okay? Okay, and the magnitude on the ket y here is omega, our nth root of unity, to the minus yt. Okay, so this always has magnitude 1, independent of the value of t or y. Okay, so that means that all non-zero entries of the Fourier transform GT have the same magnitude. Okay, so that's one important property of the Fourier transform. The second important property is that the jth entry is non-zero if and only if j is equivalent to 0 modulo n divided by s. Okay, so those are two critical properties of the Fourier transform GT. Okay, so I'm going to prove this to you in a minute. This basically relies on the key lemma about the Fourier transform that we, well, about multiplicative characters, really, that we saw in previous videos. But before I prove this punchline, let's just finish the proof that Shor's algorithm works, and the algorithm that we've described works in this simple period finding case, given these two properties. Okay, good. So the fact that all entries of the Fourier transform of GT have the same magnitude, and that the only non-zero entries are those entries j where j is equivalent to 0 modulo n divided by s, what that means is that if we measure the Fourier transform of one of these GCs, then what we're going to see is an index j such that j is of the form k times n divided by s for some k chosen uniformly at random in 0 through s minus 1. Okay, so we have to see an index of this form because of this second property, okay? And because of the first property, because all the entries of this form have the same magnitude, when we measure, we're just going to see one of those entries uniformly at random, okay? And the other very important thing, remember that we have no control over which value of f we saw when we measured as part of the second step, okay? So the nice thing is that these two properties, it's totally independent of what t is here, okay? It doesn't matter. So this is true for any t, as we just saw in the demo, right? So all the columns of y had the same property. Okay, so that's also critical to the algorithm working. Okay, good. So this punchline, it establishes that when we measure, after the third step of the algorithm, after we apply the Fourier transform, we're going to see an index of the form k times n divided by s, where for some k chosen uniformly at random. So the interesting thing now is that as long as k is not equal to 0, then we're going to learn some information about s. Okay? And it turns out that just a few samples, a constant number of samples, is actually going to allow us to completely recover S, with high probability. Okay, so let's first just handle a kind of boring case. That's the boring case where K is 0. And basically the point here is that as long as S is big enough, what's the probability that K is going to be 0? Well, this set here is of size S, and we see an element of it uniformly at random. So the probability that K is going to be 0 is just 1 over S. Okay, so as long as S is big enough, that probability is going to be small. And the point is that if S is small, like if S is less than or equal to 5, we can just directly handle that case, just by querying f of 0 through f of 5. So if we query that and we see two values that are the same, then we know what S is. Okay. So now we can assume that S is bigger than or equal to 6. And then the probability that we see K being 0 is at most 1/6. Okay. And what we want to do is just repeat this whole quantum procedure, the 3 steps of this quantum algorithm. We're going to repeat that 5 times. And our goal with repeating that 5 times is to get 3 non-zero values of K. All right. And you can just do this simple calculation to show that if you repeat that 5 times, the probability that you get 3 non-zero values is at least 95%. Okay, good. So now let's say that we've obtained 3 non-zero values of K. So now we know K1 times N divided by S, K2 times N divided by S, K3 times N divided by S. Okay, so we see these 3 numbers as outcomes of our measurement. Okay. And now what we're going to do is we're just going to compute the greatest common divisor of all these 3 numbers, right? So you see that N divided by S is a divisor of all these 3 numbers, and of these 3 numbers here, right? And if K1, K2, and K3 have no common divisors, so if their greatest common divisor is 1, they have no non-trivial common divisor, then the greatest common divisor of these 3 numbers is just going to be N divided by S, okay? And we know what N is, so if we know N over S, then we can recover S. And we can compute the greatest common divisor of these 3 numbers. We can just do that classically in like log n time. Okay, so that's not a problem. Okay, so basically we're in the good case if these 3 random numbers that we see between 0 and s minus 1, k1, k2, k3, well, we don't actually see them, but they're implicit in these numbers that we do see. But if the greatest common divisor of K1, K2, and K3 is 1, then we're done, right? So now we just have to estimate the probability that this happens. Okay, so what is the probability that a prime P divides K1? Well, again, K1 is chosen uniformly at random. So the probability that P divides it is going to be 1 over P. Okay. And each of these K1, K2, K3 are chosen independently at random, right? Because how do we obtain the K1, K2, K2, K3? It's by repeating this quantum procedure multiple times. Each time we see an independent result. Okay, so that means that the probability that a prime P is going to divide all 3 of them is 1 over P cubed. Okay, so now we can bound the bad event that there's a prime that divides all 3 of them by union bound just by summing over all primes of the probability that that prime divides all 3 of them. Okay, so that's like the sum over all primes, 1 over p cubed. Okay, and we can upper bound this just by writing out terms for the first few primes here explicitly, okay, and then just bounding the rest by summing over all integers, that are bigger than or equal to 11 of 1 over t cubed, okay? And now 1 over t cubed is a decreasing function on this interval, right, for t bigger than or equal to 11. So we can upper bound this term here, this sum, just by the integral from x is 10 to infinity of 1 over x cubed dx. Okay. Okay, so this we can just explicitly compute, and we upper bound this sum by 1/5. Okay. So that means that with probability at most 1/5, we will be in this good case that the K1, K2, K3 that we see from the algorithm, their greatest common divisor will be 1. Okay, so just to summarize everything now, first we have to handle the bad case where S is very small, like at most 6. So we do that just by querying the first few values of F. Okay, so if we don't see a collision there, then we know that S has to be at least 6. And then we just repeat this whole quantum procedure, say 5 times. Okay, so the total number of queries we make is 11. And now each quantum procedure requires 2 applications of the Fourier transform. So we can do that with order log n squared many gates. In the classical reconstruction, we just have to do compute a greatest common divisor. So we can do that in time order log n. And our success probability is at least 75%. So we lost 5% from the bad case where we see an outcome of 0 too often. And then we lost 20% from this case that it might not be that K1, K2, K3, that their greatest common divisor is 1. Okay. Okay, so that's everything. So with about 11 queries and a quantum circuit of size order log n squared, with these oracle gates as well, and classical reconstruction time order log n, we can find the period of a simple periodic function.